So the choice I've made for the third lecture is a recent project that I have been doing with the group of the University of Buenos Aires. I'll say a few more words about it in a minute, but it's the mean field opinion model. So it's related to a voter model and is driven by the mean. So it's a mean field model, right? Okay, so a few words on the project and the team. I'm very happy to have had the chance of working with these guys. Ines, Monia, and Pablo, they are wonderful, wonderful people to work with. It has been a joy visiting them multiple times at the University of Buenos Aires. So I'm very glad for having had the opportunity. And I want to thank also the support from both Leiden and Durham University along the way. So before I say specify the model, give the description, it's going to be a continuous time Markov process, like all that. This is the theme that that we're talking about. Is we're going to treat it using martingale methods. So, but before I start entering the specificity of the model, let me say a few words about the context and what how we arrived at this project, right? So the first model for so these voter models, they are actually related to models for conflict of species that are in a dispute for a certain territory. So you might recall Hugo's talk in this morning. So there were islands of different species, and they were somehow trying to occupy a certain space, and they were in a balanced situation. So you're exchanging territories with equal probabilities. This type of disputes, they generally end up with one species dominating the other. And a natural question, and that's one that Dublina asked in the end, is, well, how long is this dispute going to last? So imagine you're invited for a game of Risk. I think you might be wondering how long it's going to take. So when we start looking into these models, they have a spatial distribution, they have some dynamics. Our goal is really to calculate in time the evolution of the probability measures that describe what territory belongs to which species. So this first model was introduced in the 73, and a couple of years later, oh, sorry, let me skip that. A couple of years later, Liggett and Hawley, they started studying the voter model. And the voter model actually appears as an application of in a more general framework of the study of ergodic theorems for weakly interacting infinite systems. So these two types of models that we're looking here that somehow have a dispute over space. These are what you have is that you're exchanging the total number of you have a kind of a novelty along the time. So you constantly change you can eventually eliminate one species of the game. But what's interesting is that not always. Sometimes you have an equilibrium, and the system is set up in such a way that you have multiple solutions. So so you can have multiple ergodic invariant measures for the system. So the system ends up not being ergodic. On the other hand, on the other side of these types of opinion models, we have so when we say elections, this is related to opinions. But now we are going to talk to something that's also another side of opinions, which is averaging, reaching consensus, finding a common ground between different opinions. And that's a very beautiful thing that happens through conversation, right? So I have opted here to show you a picture from this movie called 12 Angry Men, where the jury or the committee has to achieve a common, a unanimous decision on the fate of a certain individual, which is being judged by allegedly committing a crime. So the process of talking is one in which we update our opinions, and basically the way that Maurice de Groot does is by making convex combinations according to some sort of influence matrix. And the proof of convergence is to the mean is very much related to Perron-Frobenius theorems, where we see that the matrices, as we iterate, we see them converging to an invariant state. So another paper somewhat related to this process of talking and reaching consensus is one by Boyd and others, which is based on randomized gossip algorithms. So they're using probabilistic methods to examine to the diffusion of information in a network. They are looking for an efficient, fault-tolerant, and distributed algorithm. So the fact that it's distributed is because it's based on a gossip, and a gossip is when two individuals interact and exchange information. So every now and then, two individuals talk and they take an average of their own state. And as such, we can see the spread of information in the network. And their goal was using these randomized gossip algorithms. It's a very recent, 2000, in comparison, right? If we look at these, it's not chronologically ordered, but if we look, this is in the 70s, and now we have a more recent one talking about how to find certain means in consensus among a network. And these two perspectives, both the spatial conflict and the approach of consensus, are the driving notions that are behind the type of questions we're asking. Okay, so before, in the first talk, you might remember I told you that this figure has never ceased to give me new insight into what I'm doing, what's my research. So I want to show you once again, this is the Markov chain we're going to define. We will induce a dynamical system in the space of probability measures. So there are some question marks here, because I want to say there is an art into choosing the space where you're doing your analysis and what's the metric you're going to use. So there's much more before, there's a lot of things that are happening before we can start drawing this picture. But what I want to say is that what we're looking at is if there is a general description we can give to the long time behavior of these systems, right? We're trying to see what happens in the long term or in a shorter time scale, how the measures behave. And the way to look at them is using the master equation, which is in our case here just the adjoint action on the empirical measure. So we are going to be on an infinite state space, but no configuration will be instantaneous. So we will have no issues with the construction. And that's maybe a relief from the last talk where you saw, wow, I need to do so many couplings. It's becoming a very technical thing. This time, I assure you that there are no issues. We can go straight to the phenomena. And it's nice because we can think of start exploring different forms of convergence on this finite constructed process. So basically what we're going to look at, and I'll be done with the construction and specification of the model when I tell you what is the infinitesimal generator. And then you're welcome to think of it as just a recipe for the clocks and the rates at which they ring. So that's the question. And our goal here will be not to completely describe this evolution, because it's difficult to take the exponential of this operator. We have infinitely many states. How we're going to make this operation is difficult. So what we seek here is to obtain a qualitative understanding of the behavior of these measures. And basically, what we want to do is try to find the right scale and the right distance so that we can observe the phenomenon we're interested in. So for distances, there are many available. They somehow talk to each other. They are equivalent sometimes they are not equivalent. Infinite state spaces have non-equivalent metrics. So there is an art into choosing that goes into choosing the metric we're going to study. I'll say a few words about this later on. Good. So that's our setup. And now we can start looking into the construction of our model. So there will be many individuals in the population, but first I want to say what's happening to a single individual. If we understand what's happening to a single individual, which is depicted here in some point between 0 and 1, and if we understand what's happening to this individual, we'll be able to understand what's happening to all of them in this case. So this is the starting point. So what's an opinion? That's a very deep question. An opinion for us here, we're going to take as a parameter that modulates your response to a certain binary question. Say somebody stops you on the street and say, yes or no, do you think we should, do you think candidate A is better than candidate B? And then you have to make a choice, like binary choice. Then with 0 and 1 here are just these answers that you can give. So you can only give an answer that's either 0 or 1. But maybe your opinion is not exactly that you're 100% agreeing with with the proposal or the statement of the question, but you have some sort of doubts. So to model that, we're going to say that individuals will respond to the question by throwing a coin. In this case here, our individual is lying exactly in the middle, so he throws a fair coin, and then after the result, he decides where he's jumping to. So these events, this would be a simple pooling process if the evolution of the opinion, if there were no evolution of the opinions, but we are interested in allowing the opinions to change. And how do opinions change? So you see here a clock, it's my exponential clock. So when a clock rings, the individual is going to look for someone on the street, ask a question, not necessarily a person, could be just a reference, ask this reference what's their opinion on the subject, and depending on the answer, say you hear the response 1, then you're jumping to the right, you're adopting partially the new opinion that's given, or if you hear the opinion 0, you're moving towards 0. So we are adopting a conformal posture. So we are accepting the opinion that's given, and we're moving in this direction accordingly. We're going to see that there is also, we're interested in tuning the parameter. So this is going to be a convex combination with the answer that's given. It's an alpha convex combination. So, so basically now what we can do is we can write the generators. The first time we write the generator here. So the generator tells us that we have a transition with rate 1. So r plus 1 minus r is equal to 1. And is important, r is a number between 0 and 1. R is between 0 and 1. So this is the rate at which we update our opinion moving to the right is r. And the rate that we update to the left is 1 minus r. It depends on the answer that we receive from our reference. Right. So the complete model, we have n individuals in the population, and every individual carries a clock that's independent in their wrist. And when the clock rings, the same thing happens. You look for someone uniformly in the population, and you ask a question. Are you pro or against this type of, are you 1 or 0? Then you can receive an answer. And this answer is going to change your opinion. We're assuming alpha to be positive. If you're taking alpha equals 0, so you have no, you do not update your opinion at all. And if you take alpha equals 1, you adopt the opinion that you just received. So we want to look into intermediary values, people that are adjusting their opinion gradually. So the point of writing these basic transitions here, individual X jumps to the right. That's what it's saying. Individual x jumps to the right. And here, individual x jumps to the left. So updates with the value 0 at the boundary, right? The point of writing them in this compact form, the gradient of the function here, is that this allows us to write explicitly the generator and to have already complete the specification of our model. So, so very well. So what's interesting to see is that we're choosing one individual from the population to ask a question uniformly, and that's where the term 1 over n is coming from. So it acts here, and it acts here as well. That's what makes our process actually be equivalent to one driven by the mean. So even though there might be no one in the population that holds the mean opinion, the evolution of the process is stochastically equivalent to the one where we consult this average opinion with rate 1. Each individual looks at the average opinion with rate 1. So we could think of the model like this. All right. So do you have any questions about the construction of the model or the dynamics? Because it's really using the clocks, the clock wait and jump procedure, or if you want the multiple clocks that we talked about. So if not, please come forward if you have any questions. But if not, I would like to tell you the results that we have found for this model. And these are basically related to what happens to the mean and what happens to the population in the long term in different scales, actually, not necessarily just as t goes to infinity, but also as n goes to infinity. So a parameter that we're going to be interested in here is the size of the population. So as the population grows, we want to tune the alpha parameter that is regulating the convex combination. We want to tune it, make it a little less weaker. And the reason for that, you understand, it has to do with making in such a way that we really get our phenomena in the same scale, in the right scale. So it's some sort of an art. What we're looking at here is the evolution of the vector that contains all the individuals, all the opinions of the individuals. So here I'm using this notation here, eta, to be the vector of the population. Eta 1 is the opinion of the individual 1. Eta n is the opinion of the individual n. We could have named them in another way. So I just borrowed this because because we're also borrowing a lot of intuition from other models that are dealing with particles. So interacting particle systems usually have their states with eta. So that's where the eta is coming from. All right, but it's difficult to compare what's happening to vectors of different sizes. How do we compare different size vectors? So the idea is actually to project these vectors into the space of measures. Make this is an injective function. So if you have a Markov process and you make an injective function, you have a Markov process with other names. So it's the same thing. We didn't change anything. So we might as well study the evolution of the empirical measure. So that's not exactly an injective function, because you could have different vectors that give the same measure. But if you know the number n, you know how to recover the values of the individual opinions, right? And now that we are all living in the same space, so that was the question mark that we had, where we're living in the space of positive measures in 0, 1. Now we can choose a distance to investigate the evolution of this process. So the distance that is of our choice here is the vague distance. It's not a vague distance because we are not sure about how we're choosing it. It's really called the vague distance because it captures convergence up to the concentration of mass. In a compact space, the vague distance is equivalent to the Prohorov metric, the Levy-Prohorov metric, the Wasserstein distance, and other distances that you may be interested. But in the infinite line, that's different. We need to make sure that we are living in a compact space so that we can say that convergence of the vague distance is still meaningful as a weak convergence. But in our case, since we start here in a compact space, the vague distance is very handy because it allows us to deal with test functions instead of more difficult ways of measuring distance. Right. The first result is that if we have convergence of the initial condition to a certain profile, say, this is our family of individual opinions. If they are converging to a certain limit, in the limit to a certain profile, say, then along the time interval 0t, the distance, the vague distance between the evolution of the process speeded up by square root n will converge to 0. The distance with respect to this deterministic evolution will converge to 0. So what are we saying here? We're saying that our process is all the noise that we had in the process, the randomness is going away, and we have a lot of large numbers. And this convergence here is known to us because we can say what is these dynamics here. It's actually we could write this as a partial differential equation, but it's better to write as a transformation map because it gives more intuition to what is happening. And it's also, we can also apply it to measures that are not absolutely continuous with respect to Lebesgue. So that's the map. The map T here has a fixed point, R. This point stays fixed, and this is the initial mean of our process. And the other values, they are concentrating around the fixed point with rate with an exponential speed. So this is just an illustration of what's happening. As time goes by, we are concentrating these values. So that's exactly how we can get a sense of why this result is true. So I want to give the results. I don't want to enter very much in the technicalities, but I want to say a few words about how we could make sense of this result. I want to give some intuition. So the intuition for this result here is that we have a contraction. The contraction appears if we, for a moment, forget that individuals are jumping at different times in different directions, and just say all individuals jump together in the same direction. Let's make an absurd claim for now. Say all individuals jump at the same time in the same direction. So when this happens, if two individuals jump in the same direction, then their distance is reduced by a factor alpha n. And you see here, alpha n is 1 over square root n. So let me write here 1 over square root n. And at time n square root nt, sorry, the number of jumps that we had is square root nt. So this explains where this factor is coming from. We are contracting that much because we could think of individuals are jumping roughly all of them in the same direction, and that's causing their distance to contract. So the challenge really is to prove what's the fixed point of the system. So proving what's the fixed point is another story, but it already gives us a good sense of what's happening to the system if we're able to slowly show the stochastic equivalence between the model that we have described and this, let's say, reference model that has deterministic jumps. Not all of them in the same direction, but all individuals jump together in the same direction, but not always in the same direction. So sometimes everybody jumps to the right, sometimes everybody jumps to the left. So, okay, this will give us an equivalent description of the process. So we see it's interesting at this scale. The process is the noise is going away. The process is showing some sort of stability. at the mean. The initial value here, R, is driving the system to concentrate its mass in the long term, or at this scale, at a Dirac delta in X. So this is what we call consensus. It's very much related to the two type of problems I spoke about in the motivation or the background slide. That individuals have they have talked among themselves and they have reached a consensus. They have made their opinions equal. So the model seems at first to be very, very trivial, in the sense that all the opinions are converging to the mean and that's what's happening, but that's not the overall picture. So to go on, it's interesting to study the long-term behavior. Mind you, what we were looking there, it was for n going to infinity over a finite time horizon, even though we were speeding up time a little bit by square root n. Now we're going to take a different approach. Let n be fixed, and let's take t to infinity. What happens then? Well, then what we see is a very different story. So what we see is that the mean is going to the boundary, either 1 or 0. And if the mean is going to the boundary, this means that every time you're asking a question, the answer you're hearing is the same. So if the average is going to the boundary, what this means, to the boundary 1. If it's going to 1, what this means is that we're always hearing the answer 1. So even though the system is not quite there at 1, it's impossible to reach exactly 1, it behaves as if it was the state 1. So we say it's absorbed by 1, so it has converged to the boundary. So what's interesting about this theorem here is that we can say the probability with which this occurs. We can say that the probability of going to the boundary is exactly the mean that we started from. So that's the initial mean opinion is the one that is regulating the likelihood that you eventually converge to the boundary 1. So, and the answer for this, how we can get there, you might already be guessing. The answer is, well, there's a martingale. And as Hugo told us, a positive martingale always converges. And in our case here, convergence has to be convergence to the boundary, because otherwise we are in an irreducible component of our system, and we would not have converged. So essentially, with a one-line argument, we can see that the process will eventually go to the boundary. And I have taken the liberty here of making an artistic depiction of what is going to happen. There is some sort of noisy behavior, but eventually you go to the boundary. Right. So the second result is the following. Well, if the mean is going to the boundary, this means all individuals are going also to the boundary, because the mean cannot go to the boundary if one individual decides to be away from that specific boundary. So by looking at what happens to the mean, we can give a description to what happens to every individual. But what we want to do is to capture this. There's something very strange that happened. We were fixed, the mean was fixed, and then as we allow t to go to infinity, the mean is going to the boundary. So can we give a description of what's happening in the intermediary? Can we get an intermediary description? Can we capture the motion of the mean? So that's the question. The answer is affirmative. We can, and actually it converges to the solution of a particular stochastic differential equation, which may be familiar to you. It is the Wright-Fisher diffusion, which is a universal object that appears again and again in all these models that relate to population dynamics, spread of infections, and well, let's say it's a version of the Brownian motion in torus absorbed at the boundary. So the way this appeared here, and let me just add a picture. The way this appears here is because individuals somehow are adopting the type of their ancestors or their peers. So their peers. They look for someone in the population, they adopt their opinion, and that's very much like the modern models where you adopt the type of your ancestor. And that's basically what's happening here. I'll give an argument for that later. I don't want to go in detail now. I want to give an overall picture of all the results, but I will then say a few words about why do we see the right Fisher diffusion here. All right, but it's worth saying that the scale is captured in this theorem. It's not square root n, as it was in the hydrodynamic limit. It's not the infinite time range, but at scale n squared, then we know what type of behavior we should expect for the mean. It should be oscillating like a right Fisher diffusion. So we shouldn't take this as a deterministic trajectory. This is an illustration of the outcome of one random thing. But if we only know information up to a certain time, then the thing can go in many different ways. So it's really, it really depends on what is the noise that will drive us. And we know that this eventually will reach the boundary. So we know that the boundaries are accessible for the right Fisher diffusion. So, right. The final result is one that looks back at the individuals because the population is composed of individuals, and this individual fluctuation is really what is driving the mean, what's making the mean fluctuate and eventually reach the boundary. So we want to look back and say, well, can we say something more precise about what's happening to particular individuals in this population? Well, if we want to say something meaningful, we need to get the scales right. So we want to zoom in and look closer, look at the deviation from the mean. So we're zooming, and we're now looking at another type of empirical measure, because these guys here, they live in the space of measures in R. These are positive measures, but in R. The D could be negative. So we want to study what's happening to them. And the answer is that actually the process, the evolution of the dispersion of these individuals around the mean is closely related to a process that's the Ornstein-Uhlenbeck. Let me see, Ornstein-Uhlenbeck. I'm writing it because a friend of mine always asks me, what is what is OU? What does OU stands for? So it's this pair of researchers, Ornstein-Uhlenbeck. So, but basically, for now, if you don't need to worry about this. Just think of it as a Gaussian random variable with that variance, specific variance R1 minus R over 2. So the theorem is that our empirical measure converges in probability if we can keep track of the value of, remember that this is a random thing, or essentially it's going to be fluctuating as a right Fisher diffusion. But if we are able to know what is the value of the mean, then these two processes, the distances between the dispersion and the Ornstein-Uhlenbeck law, here is a W for Wasserstein metric, should be vague. My apologies. Sorry. So this is the vague distance. We'll go away. Let me just, this is vague. Well, there you have it. It's a V. And another thing is we can see from this result that the dispersion is the maximum at 1/2, because as we go to the boundary, this function R1 minus R becomes smaller and smaller, right? It achieves its maximum at 1/2, and my drawing is not perfect, it's far from it, but the maximum is at 1/4. Here is 0. It's a very important function, this R1 minus R. Actually over 2, so this would give an 8, right? Sorry. But R1 minus R is 1/4. Okay, so that's the image that we have for our process. I want to sum this up. Basically, the hydrodynamic limit here is a convergence to a delta. The long-term behavior is convergence to the boundary. At the scale n squared, the mean is converging as a right Fisher diffusion. And then we can say something about the fluctuation. Actually, we can also combine these two results, the fluctuation and the dispersion, into a unified picture. So let me just say here that this is the hydrodynamic scale. So n scale, the scale is square root mt, n is going to infinity. Here, n is fixed, and t is going to infinity. Here is for the mean, right? Here, these two are for the mean. This is the mean. This is the mean. So this is n going to infinity, but the scale is n squared t. And this lives in some sort of mixed scales. So I won't go into detail, but this is for the population. So this is for the population. This is also the dispersion of the population. So this is the picture that we have captured multiple phenomena in different scales of our process. All right. So let me give you now, as promised, a few ideas on the proof of these two results. Let me go back. So I want to give some proofs about this result and this result, and that will then we'll be done. Right. The fluctuation of the mean. You know, at any scale that is faster than square root n, we should imagine that all individual opinions have coincided. They are moving essentially like a Dirac delta. So it's not such a great assumption to think that all individuals started with the same opinion. Here, let's say all individuals have the same opinion, RT. And we're also simplifying very much our picture. We already seen that it's almost as if individuals are all jumping at the same time. That's an approximation. It's not exact. When we amplify the scales, this type of approximations break down. We cannot consider them anymore, but let's consider them for now. So let's say at a given time, we have the transitions, and the splitting that we have of our population is regulated by RT. So this is going to tell us how many individuals jump to the right, how many individuals jump to the left, right? Turns out it's not really the fact that individuals are jumping at different times that is the approximation that makes all the, let me say this first. If we have a perfect splitting, this means that the new mean the mean is conserved. And that has to do with the fact that RT is a martingale. So perfect splitting, in average, that's what we have. A perfect splitting will change the mean, will not change the mean. So, right. Then what I was saying is that the truth is that the relevant noisy phenomena is not the instant at which individuals jump, but where the individual is jumping to. So what type of splitting we're having. So each individual is going to ask the reference or a specific individual from the opinion and then update their opinion. So what we really have is a binomial random variable, and what we have considered with the perfect splitting is the average. But their difference is a random variable, and we know typically how it behaves. It is almost by the central limit theorem Brownian standard Brownian motion that has this variance and this scale. So that's the type of noise that we're seeing. So ET is converging. So we could have a parameter here n, and this is converging to normal 0, 1. Right. That's what happens in one single step. So if we incorporate the error in our computations, we see that the effect on the mean is of order 1 over n. So that tells us that at the scale t, the squared, the variation of the square, we're looking for the quadratic variation, right? So this is of order 1 over n squared, and here e squared. So this is 1, right? Because as we spoke, it's a normal random variable 1. So the variance here is 1. So if we, so let me ignore this for now, because the 1. If we speed time by n squared, we can start observing, we can cancel the denominator, we can start observing a certain macroscopic feature in our model. We can start seeing the fluctuation. So we can get the intuition for the scale just by making this qualitative analysis of how is the splitting behaving. And that's eventually, the rest of the proof is eventually making the substitutions and writing the integral formulas, a martingale representation. At the end of the day, we recover this as the typical quadratic variation of our continuous martingale, driving our continuous martingale, and we represent this as the right Fisher, and this turns out to be the right Fisher diffusion. But right, we got the terms right already with this scale, so that's making sense of our result. The next result the next proof I want to talk about today is how do we get the dispersion of the individuals around the mean. And the way to do this is, that's the key result, is to analyze the typical concentration of the typical distance of the individual's opinions around the mean. So I'm calling this the typical concentration of opinions. And we see that this is of order 1 over square root n. And that tells us that if we zoom this by n to the power 1 over 4, we should start to see some macroscopic changes. So it's, again, the same heuristics. You want to get the magnitudes right first, and then you want to get the details correct. So to get the details, we need to write the integral expressions for test functions of our empirical measures. So we go back to the scale square root nt, and that's the evolution that we observe. So when we test, this is the test function. When we see the value of the test function at time t, we're scaling by square root n, but that's essentially how you should think. The process at time t is an integral. We have an integral formula for it that has essentially here the terms of the right Fisher diffusion of the Austin-Uhlenbeck, sorry, of the Austin-Uhlenbeck dynamics with a certain variance term. So it reminds us of the right Fisher coefficient, but that's not it here. So this here is a thinking martingale and some other terms that are negligible. So we manipulated this formula very much so that we can get to this nice expression. And then the next step is to compare it to the evolution of an Austin-Uhlenbeck process with initial known mean. And that gives us a very similar formula. Then when we compare their difference, once we show that this noise term vanishes, and we also need to work out the compactness of our space, we can get a convergent subsequence Mn to M2. It's like a tightness argument now. We're going to a subsequence, seeing that this is convergent to a certain limit point. The question is, how is this limit point behaving? Well, for any test function, it will satisfy this equation. But there's only one solution to this problem, and that's the measure 0. So we have proven that this distance here is going to 0. So this difference here is going to 0 for every test function. That is telling us the convergence in the vague metric. Right. So the last step in our talk here is to get the image of the, or to combine the dispersion and the fluctuation results. So we have seen these two things. We have seen that the mean is diffusing like a right Fisher, and we have a dispersion picture for the population. So there's a way of putting these two things together. It's not going to be a result, a convergence in probability. It has to be a convergence in law, because this is in law. This result here was in probability. So when we try to combine the two, the most restrictive one is the one that wins. We have a convergence in law to something that really captures that behavior. And that's when we combine the two scales, we have that the mean is converging to the right Fisher diffusion, right? Fisher diffusion. And the other coordinate is also converging. So we can have a convergence in the product space to the Austen-Uhlenbeck process. So this is the equilibrium measure of an Austen-Uhlenbeck process. And that's where the term R1 minus R over 2 comes from, regulating the dispersion. All right, so I'm about to finish. I just want to conclude with an overall picture. It's very similar to the one that I showed you already twice. You might be already, oh, I've seen enough of this, but I think it's very, very worthwhile looking at it again. So this is the space of measures, right? We have figured out that's the space of measures in 0, 1. We have many different initial conditions that we can have here, empirical measures. Many different empirical measures with the same mean. We see that at the hydrodynamic scale, so this is the hydrodynamic. Or if you want, it's the scale for the law of large numbers, right? At this scale, which is t, is actually square root nt. It's a very vague statement. We have a convergence to a Dirac delta. So all these different configurations, they might have the same mean. They converge to the Dirac delta. Then, as we speed the process a bit more, as we allow time to go further, so we go to the diffusive scale. We have t of order n square t, right? So that's, we start to observe that the mean is drifting. So it's diffusing, actually. It's diffusing, and the long-term behavior of this is convergence, eventual convergence to the boundary. So that's the long-term behavior. Actually, our system is transient because we're leaving every compact space and we're not really entering the point 0. That never really happens. For any configuration that doesn't start from 0, we never enter the site 0. So, and with that, I think the beauty of this model is that it contains several nice features. It is not difficult to build this, very sympathetic model. We can observe what I'm calling metastability, which is when the system tricks you into thinking it's converging somewhere, but actually in another scale, the behavior is different. So I think that's a very nice problem that has many, many open questions related to it. We could allow for another question. We could add gradually in our system new opinions and allow the system to evolve in a complex or in a simplex. So there are many variations that one could consider and that are interesting. So so thank you very much for the opportunity, for coming here, for listening, and for the interest in this field. Thank you so much.
Right. Thank you, Conrado, for the third lecture. Is there any questions from the audience? If not, I can ask, maybe it's not a question, but I want to know more about the variations that you said at the end of just before this slide.
Right. So Well, a variation that one can consider is whether we take individuals to be conformal or anti-conformal, because when we're talking about opinions, we usually have the phenomena of things that reappear, like patterns that go and go away, vanish and come back. So to what we see here is that eventually all the dynamics loses its activity, because we're getting eventually to the boundary, and the dynamics becomes trivial, right? So a way of adding change to the system, there are two ways of adding change to the system. One is having some individuals that are kind of suspicious of the answer they receive. They are countercultural type of individuals. If you say one to them, even though you may be very kind and very sympathetic as these individuals are here, I think they're very nice. So you may hear the answer and you're actually saying, you know what, I'm jumping against it. I'm moving in the opposite direction. So that's one way of modifying the model, of changing the model, so that we still have a persistence of the dynamics, or we see some oscillations. That's one. Another one is adding communities, where you say, well, depending on the person who is answering, I am being conformal or anti-conformal, right? So you can be suspicious of certain types of people, and you don't want to trust them. So you can have all variations in terms of trust matrices, very much in the spirit of what De Groot makes. So he had a matrix of how much you trust in a certain individual, and that matrix was driving the consensus. So here as well, we can take influence matrices and change the way we update. So the final way that's also possible of changing this model, there are many others, but another one that I think is interesting is to add mutation. So new opinions can appear. So in population dynamics, new mutation is something that happens, and it's physically meaningful. Also in behavioral systems, new opinions are coming in the game. So to deal with different new coming opinions and what it does to the system could change very much the analysis of our model.
Right. So in this case, would it still converge to some process?
Depends on the rate at which new opinions come. So if you just add mutation and the mutation brings you back to the line 0, 1, so that's it's well known that the Moran model, for instance, with mutation, has a unique invariant measure. So you can examine the convergence to this invariant measure, and it's tricky because there are many things happening. You are adopting the type of your ancestor, but you're also subject to mutation. So you have to tune in the rate at which mutation is changing. But you can see convergence of these families of processes to the invariant measure of the system. So mutation is a way of making the system forever changing. And the mutation can be of coming back, right? It's not like a new type, because if you add a new type, then you have to increase the dimension of your problem, or allow you to live in an infinite possible space with all possible types. And then you are going to try to make sense of what is the trajectories that you're observing. And it will depend on the rate at which you see mutation. If mutation is too big, then the invariant measures will look very much like random. If the mutation is not too big, then you see it, and then you see some features of the resampling playing a role into your invariant measure.
Okay. Thank you very much. Is there any questions from the audience?